Hello, everyone. Welcome back and welcome again. Welcome back to Particle Physics for Teachers. This is now our fourth session of the course, and I'm thrilled to be introducing you to my friend Marco, who's joining us from Neuss in Germany, where he's a teacher. As I've mentioned before, when I was over like what sessions to expect, this is one of my favorite members on what goes on with tracks, like keeping track of the tracks or understanding the paths that particles made was the most useful explanation I've had of it. So getting to share that with other teachers, for me, that's just perfect. And to mention as well, those of you who were with us for the visit of the Atlas detector Friday, you know how Steve kept mentioning that particles curve in magnetic fields? That's why they have the huge toroidal magnets. Hopefully, if you don't already understand perfectly everything Steve said about that this will give a good understanding of what's going on.
Okay, thank you, Michael, and thank you to everyone being here today online in this workshop about the small invisible things. So before we start, I just want to shortly introduce myself. My name is Marco, and Michael said it, I'm a teacher in Germany, and my subjects are mathematics, informatics, and my favorite one is physics. And I met Michael at CERN in 2018 at the ITW, and it was a great experience. And already before, I liked particle physics a lot, but then I started loving it. And what I want to do today is introduce my very favorite detector to you. So the basic topic of today's sessions is about detectors, and I thought about two parts of this workshop. The first part is I want to talk about detectors, and I want to do it in a way I do with my students. So we do a live example of activities you can do in your lessons to teach detectors. And the second part of this workshop will be, we will look at a special detector, more a little bit later. So if you have any questions, please feel free to write them down into the chat. I hope I can read along during my presentation. If not, Michael will help. And if you see any questions, Michael, I don't see, please interrupt.
Of course, yeah. And I'll wait till what seems like a logical time to interrupt you. But yeah, if it seems, yeah, of course.
Okay, I hope you can see my slides on your screen.
Coming through nice and clear, yes.
Now, okay. So, okay.
Perfect.
So, what do I want to do with you today? So, particle physicists always want to try to understand the universe. And what do? They are searching for elementary particles. So, very, very small particles no one can see, but they try to make them somehow visible. So they have three great questions. So the first question is, where are we from? The second is, what are we? And where are we going to? So I won't answer any of these three questions today. So if I could, I wouldn't be a teacher anymore, but get a Nobel Prize or something else in my shelf. So let's go to the problem. No one has ever seen these particles, which might be the solutions of these three questions. So when we look back in history, we start with Greek philosophers. So long time ago, they first had the idea that all matter is built of atoms, those small, undividable things. Then in the early 20th century, everything went fast. So they thought, okay, such an atom is somehow dividable. We have a nucleus, which is positively charged, and we have electrons, which are circling, however they do this, around the nucleus. And in the 1960s, they found even more particles inside the atom, which are the quarks, which make up the protons and the neutrons. So when we talk about the size, well, the Greeks may say small. Early 20th century, they were at a scale of 0.5 times 10 powered by minus 9 meters. And in the 16th, they actually found it's much, much smaller. We talk about 10 powered by minus 18 meters. So how can you see such small things? Well, short answer, you can't. But I want to do first activity now with you to get an imagination of which size we are talking about. So I have a link here. I want to copy this one to the chat, and I ask you to open this link and just watch the video, which is hidden behind it. I get the first reactions in the chat that you have already watched the video. And there are two reactions. They're using the word amazing. And I think it is what CERN did there. They made an amazing video. And this is the reaction the students really show when I show them the video, and they can see, wow, we are talking about something very, very small. And you can see the scale. It's hard to imagine what particle physicists are doing and what they are searching for. And so we could give the presentation the next step. So how can we see this? So we need something which we call detectors, and the word detector is derived from the Latin word detectare, which means to discover, to find, or to trace down. And this is basically what detectors do. And this leads us to our second activity, and I asked you to use the chat. Everybody has and uses detectors every day, and I would like you to write a private message to me in the chat and give one example of a detector at your body and what it detects. We get plenty of answers here, and I think everything you just wrote down in the private messages is pictured on this slide, and this is exactly what the students say, so they know detectors already. And if you look at our body closely, so all this you wrote down and what we've here on the slides, so our brain is the thing which makes the information from the things we detect. So if you have visited the virtual science camp about the Atlas detector last Friday, they might have told you something similar. So Atlas consists of many parts, and each part has a special task. So like the eyes detect light, we have a tracer which detects the path of the particles which are produced. And then there is a big computer which is making the best all of this information the detectors collect, and so people can work on it. So every one of us uses detectors. A third activity. So I found this nice picture on the internet, and I would just want to ask you, which information does this picture provide? So now this time, please don't use the chat, just use the microphone and say what is your idea about the information you find in this picture.
Someone has been walking.
Yes. What else?
Trajectory.
Mm-hmm.
Different depths of the prints.
Uh-huh.
There are also animal footprints.
Mm-hmm. So we can get plenty of information from this picture. For example, you said there are people. No, it's wrong if I say there are people. There were people which moved along the beach. And there were animals which moved along the beach. And from the footsteps, you can get more information. For example, some are deeper, So there might be an information, there might be a heavy person which have been there and walked maybe this way. And so we can draw some conclusions about the traces the people or the animals left on the beach. And wouldn't it be fantastic if detectors would do the same, give us such a nice picture, and we can look at it and say, wow, this happened. There was this particle, and this was another one, and it did behave somehow very different. So this would not only be fantastic, but I will show you in a few minutes. You will get those pictures, and you can look at these pictures and draw conclusions about what happens there. So I just want to summarize what we did so far. So in this activity with the picture on the beach, we know that someone went along, but we don't know who it was, how he looked or she looked. We have no idea, but we know someone was there. And this is exactly what particle physicists do with their detectors. They just see something was there. So they detect the traces. And the other activity we did first was we have several detectors on our body, and every detector has a special task to do. So here we go. Now we do a little bit of particle physics. I took two pictures at CERN. On the left side, you see the big European bubble chamber. And the bubble chamber is a detector which is my most favorite one, and I'm going to tell you in a minute how it works, and you will see you can explain to your students easily. So this detector is more easy, much more easy than Atlas or CMS. And on the other side, you see this massive block, which is part of this detector and will go down into this part. So maybe you will understand later what I mean. If you get some informations, or if you want to get some informations, check this slide. So this one is about 26 tons, so quite heavy. And it worked from 1973 to 1984. So it's quite a long time for a detector, and it did some great efforts to bring the particle physics to where it is today. So they found some particles which were stated to exist by theoretical physics, but they found them in the experiments. And they also did some neutrino physics, but I don't want to go into the details now because this might be a very long workshop if I do so. So I painted a bit. So this is a very simplified sketch of this detector of the bubble chamber. So it basically is a chamber which is filled with liquid. So we are talking about this detector today using liquid hydrogen. And this is inside this box. And this box has windows on the one side and on the other side, and there are cameras and flashlights. So this detector is all about taking one picture after the other. Something very similar to the beach, which was basically a picture, and this produces pictures as well. So what else do we have? We have a beam of particles which is shot into the chamber, and we want to try to find out more about these particles. The chamber itself is situated in a magnetic field. So why? Maybe you've learned in the Atlas workshop before, but I will tell you later. And then there's another part, a very heavy piston, and I go back to pictures here. So this is the piston you saw on the drawn picture. So what does this thing do? It is basically something like a syringe. Everyone might have at school one or two of them, and everyone can use this syringe to understand how this massive machine works. Now I want to show you a video about this experiment I talked about. So I filled a syringe with warm water, and I removed all, or at least close to all air out of it, and pressed a finger on the opening, and then I moved the piston. So what happens? You can see in this short video. So when pulling out the pistons, you see a lot of bubbles in the water. And do this again. So any idea what these bubbles were coming from? I see 2 answers in the chat already. Exactly, it is boiling water. And it is because of the pressure. So by pulling out the piston, I reduce the pressure in the syringe. And you all know if we have a lower air pressure, we can bring water to the boil by a lower temperature than 100 degrees Celsius. So pulling out the pistons brings the water to the boil. And if we compare this to the bubble chamber, it is the same. So we can bring the liquid hydrogen in the chamber to the boil and make a lot of bubbles. But this is a problem. So if we have a lot of bubbles in the chamber, we won't see any particles or any traces. So what happens is they don't bring the liquid to the boil, but short before this. So it is in a state which is quite unstable. And if you add a little bit of energy, then it will start to boil at the place where you deposed the energy. And this is why this machine is called the bubble chamber. So you have a liquid which is close to boiling, and then you give it some energy by shooting charged particles through it. And this means these charged particles leave a trace of bubbles. Okay, my slides are working again. So they did stop for a moment. Yes, okay. So, and I just talked about pictures and pictures and pictures. And what you see here is an original picture made from the cameras at a bubble chamber at CERN. It is from the year 1972. And what you see is many traces here. And these are all bubbles which are left by the interaction between the beam and the liquid inside this chamber. So a bit more information about this. What you see here, these lines going from the bottom to the top, this is the ray. So the positively charged particles from the ray, and they move from the top to the bottom very fast. And what you see here in this picture, there is a lot of things happening we are going to talk about right now. So the first question is, why are those traces here bent? So this is like a spiral. And if you look carefully, you will see, okay, this is the line like a circle. So all these particle traces are not straight, but bent to the left or to the right. So the reason is, I just told you before, there is a magnetic field. And you all know, if you have charged particles, you will have bent curved if they pass a magnetic field. So some are curved anti-clockwise or to the left, and some are curved clockwise to the right. So the first thing you can see in this picture is, when looking at these traces, that you have two kinds of charge. So this is a different direction compared to this. And you all know when charged particles travel to the magnetic field, you have the Lorentz force. So I don't know how you teach your students the left-hand rule or the right-hand rule. I've heard there are different interpretations, but you can use one rule for negatively charged particles and one for positively charged particles. And this is what you see here. Particles which go to the left are negatively charged, and particles which go to the right are positively charged, because I just didn't give you one information. We have a magnetic field pointing out your screens. So you can determine the charge of a particle by just looking at the picture. So again, if we check these blue traces and the magnetic field is pointing out of your screen, you have your thumb pointing to the moving direction of the particle, which was up, and the magnetic field, you use your index finger pointing towards you, and the middle finger is the Lorentz force, which is a magnetic force which drags the positively charged charged particles to the right. And the same rule, of course, is for the red ones. So I talked a lot, and let's do a short quiz. So let's assume the magnetic field is pointing out of your screen towards you again. And can you tell me the charge of the particle which leaves the trace in the blue color? I call it trace 1. And what is the charge of the particle in the green color? I call it trace 2. So magnetic field pointing towards you, and the moving direction is indicated by the arrows. So I see in the chat there is a suggestion green is positive and blue is negative. And I also see a suggestion blue is positive, and I see blue, green, positive. And the solution is yes, both particles here in this picture are charged positively, because if we just go back to this picture, they are bent like a clockwise movement. So, and you can just keep in mind for this activity, everything which goes to the right or is bent clockwise is charged positively. So what about situation number 2? So this is the first particle, trace number 1, and the second one does this movement in blue. Okay, I see a lot of answers which say 2 is negative. That's correct. And I see some people who say number 1 is neutral or has no charge. So if this trace number 1 is from a particle which is not charged, there won't be no interaction with the magnetic field. So it would go very straight. And let's try to find a straight line here. So this might be a straight line. I hope you can see it on your screen.
So your line just barely, okay, there it shows up better. Like it showed up before, but just barely. Now it's more clear, that blue color.
Yeah. So number 1 is actually bent to the right, so it is a positively charged particle. And some more information. So you cannot see neutral particles in the bubble chamber because there is an electromagnetic interaction between the particle and the liquid inside of the chamber. So you won't see any traces of neutral particles. Okay, let's dive a bit deeper into the pictures like these 3 people do here. So they have somehow a screening machine here, and they are looking at a picture like you have seen just before, and they are trying to get as much as information as they can from the picture. And to get many information, you have to understand what you see. And I want to do it with some more pictures. So on the left, you see this spiral. I just follow it with my pointer. And it starts here at the beam, which comes into the chamber. And any suggestion what it could be, what particle might make such a spiral trajectory? Now I hear proton. I see electron. So the second one is correct, because what happens here is you have the beam. So this is quite high energetic particle, which collides with an electron of the liquid hydrogen in this chamber. So it just kicks it out of the atom and it moves in a spiral like this. And it must be a negatively charged particle because it is circling anti-clockwise. So let's go to the next picture here on the right. I call it Beat because it's something like these little balls, you know, on the table. And there's a particle coming from here. And here is a point where it seems to divide into two parts. So actually, if you look close to this picture, this trace looks a little bit different to this one. It is much thicker. And this is close to the thing you saw at the beach. You saw these deep footprints. So this is a quite heavy particles you see here. And what happens in this picture is some particle is coming here along this path and hitting a proton of the hydrogen in the chamber, and it's just kicking the proton aside, and it's just reflected here along this way. So we have some billiard game into our bubble chamber by just colliding particles and just give them some impetus, some movement, and something more might happen there. We will maybe see some more events like this later. So the next thing I want to show you is here in this picture, which looks like a palm tree somehow. I hope this animation works now. So a particle is coming from down to top, and then something happens. Like coming out of nothing, there are traces of 1, 2, 3, 4, 5, 6 particles. And I gave them a color scheme. So like in the picture before, I chose blue for particles which turn to the left. So those are particles which are negatively charged. And I used red for the positively charged one. And if you look carefully, you see a green line. I just replay this animation. So a green line is going up to the top, slide a bit right to the blue trace. So this is the particle which came from here, and it goes on like this, in this way. And something more happens. You see this kind of pink trace, which is, I do this animation again later, which is quite a thick line. And a few seconds ago, I talked about thick lines. And we have this effect again. This is a proton. So what happens here is a particle is coming in, and if there would be no interaction, it would fly along this blue trace here. But there is an interaction. A lot of things happen. There are particles produced. These are these particles, and the ones which leave those traces. The green trace is the original particle. The pink trace is a proton just kicked to the side. So this is the production of particles by a collision. And this is what they do in Atlas detector all day long. They just search for collisions and the production of new particles to find out more what they are. And let's go back to school. When you talk about these particle productions, you can check two things. So how can you produce particles? Yeah, well, Einstein says E equals mc squared. So from energy, which is located in this particle, you can produce mass, which is these two particles and these two particles. So this is E equals mc squared. And you can do another thing. So what happens with the charge? Before the process, we have the charge of this particle, which is, I didn't tell you before, which is a positively charged particle. And we have the proton, which it collides with. So we have a charge of +2 before this happens. So and after this, we can just count the lines. We have two negatively charged particles, so -2, plus the green one is -1, plus the red one is 0, plus this red one is +1, and the pink proton before is +2. So electric charge is a basic principle in particle physics, is conserved by the production of new particles by a collision. Another one, which I don't show you yet, is the decay of a photon. So a photon is obviously a neutral particle, but how does a photon decay? In which two particles? Any ideas? So maybe this one helps. And yeah, it's right. It's annihilation. It's an electron and a positron. Well, not not annihilation. It's the opposite. So we have a photon, which is decaying in a negatively charged electron and a positively charged positron. So this is what happens in this signature. So you have a point in the middle of nowhere, and then you see two traces coming from there, and you see one is counterclockwise and one is clockwise. So this again is a great example for E equals mc squared. So the photon is carrying energy, and it's gone after this process, and it produces mass. Okay, we do a little bit more of detective work. You see an enlarged picture on the left, and I want you to find traces of ionization. I want you to find the production of new particles, and I want you to find the beam particles. Just have a look at this picture. Who has found the ionization process? So an electron kicked out of a hydrogen atom in the chamber. Where do you find it? Just use your microphone and say it out loud.
Don't be shy. Anyone who has any guesses, please.
Yeah, nothing to lose.
When the spiral begins, means that an electron has been kicked off of atom.
Yes, perfect. So this spiral here, and this is a point where the electron is kicked off. So where do you find the production of new particles?
Down in 1/3 of the picture where Go, yes, and go in the middle. Where's this straight? Yes, that
Yes.
point.
Perfect. So we see particles coming from this black spot, moving to different directions, and you have to look very carefully. So here are two more traces up here and two more traces up here. And where is the beam? So the beam are all these straight lines moving from the bottom to the top. So I just highlighted the solution and you will, all right, so great detective work. Another one. Where do you find ionization? And maybe you can see a collision of particles without production of new particles.
So the ionization are the spirals again?
Yes, this is always ionization if you see those spirals. Perfect. And can you find a collision between two particles?
Maybe in the middle of the image, maybe, I don't know.
I did not understand, please again.
In the middle of the image, I think in the middle is a little particle, or I don't know, and seems to collision with the beam. I don't know.
So here in quite in the middle, yes, this is a collision. So the beam is coming from bottom to top and kicks away
Yes, there.
Particle which leaves a very, very fat trace. And what might this particle be? So this pink one, what might it be? So as you have a very fat trace here, it is a proton again, which is just kicked away by the beam. Okay, so one more. In this picture is hidden a photon, which decays in an electron and a positron, and of course, a lot of ionization. So for the decay of a photon, we need two spirals. One is going to the right and one is going to the left.
So is it the one like the big one on the right, but it actually in the middle there's like the left?
Yes, exactly. This one is part of this decay. And I think I have highlighted it here. Yes. So this one is the positively charged particle, which results from the decay, so a positron. And this one is, well, a big curve. So you can't see a spiral, but it comes from this point and goes to the left, so it must be the electron. And what you can ask now is, which one is faster, the positron or the electron?
Electron.
Why?
It doesn't curve immediately.
So you can check the curvature. Yes, of course. So from this, you can see how fast particles are. And what you can do if you have some software like GeoGebra or some other measuring devices, you can measure the radius, and you can calculate how fast these particles are in fact. So we won't do this today because this would be another class, but you can get much more information from the traces, like the speed. You can also determine the mass of the particles by using just a ruler and knowing how strong the magnetic field of the bubble chamber is. So I'm at the end now, and I gave you some links. You also get them in the handout, and I just should suggest you check them later if you are more interested in bubble chambers than before. And one of these links has a lot of pictures from bubble chambers, and you can just check them and try to find out which particles leave which traces. I know it was very quick today, so in lessons, if I do this, I maybe need 5 lessons with my students and not 45 minutes like we had today. So if it was a bit quick, I apologize for this, but I hope you got a basic idea how particle detection works. And maybe you see, like I do, the potential of teaching the bubble chamber in your lessons when you teach particle physics. So thank you very much for attending this workshop. And if you have any questions, please feel free to ask them now. And if you have feedback, please give me feedback. Thank you.
That's excellent. Thank you, Marco. And I think, or I hope we might have a couple of questions, but I just wanted to jump on and thank you before we get any of the questions, to give people a moment to think as well. And also the links reminded me for everyone I emailed the invitation to today. I forgot to include the links Steve had shared on Friday, so I'll include that in one of the next emails I send everyone else. So sorry that I missed those links, but you'll get those as well as all the links that Marco shared. As he mentioned, it's in the handout that was emailed to you, but I'll probably include it in the body of an email as well in case anyone forgets or is looking for it and doesn't remember where to find it.
And thank you for attending today. Thank you for interacting with me and the material, and thank you for the very positive feedback I can read here in the chat. I'm very happy, and I would be more happy if you try out using bubble chambers in your lessons.